Good morning. Hello, everybody. Good to see you. Happy July. Happy July. We're no longer in June. All right. There's really any notes. Oh, happy birthday month to you. Both my parents have birthdays this month as well. Happy birthday, happy birthday. I hope it's a wonderful one. All right. I think we'll start with this. That's good. That comes here. Have to swap accounts. Again. Gonna make me authenticate myself. Of course. Alright. And then we'll go to moderator view. Yeah, Cherry, I'll talk a little bit about that today. Sorry, I didn't mute my stream there. Alright, looks like we're up. Alright, so it is 11:21. I've been streaming for a little bit now, so if you're in the stream now, that's good for you. And if you're not, you're going to miss some things, but you can always rewatch on YouTube. Am I back? Hello? Can you guys hear me? My webcam is dead. Yeah, you can hear me, but the webcam is dead. Give me a second here. I don't know why my computer did that. Hope my webcam doesn't die today. That wouldn't be fun. You can just look at the top of my head. Yeah, let's see here. Oh, all right. We're back, everybody. Sorry about that. All right, so just warning you, right? I guess we had a little bit of lag there. We'll probably have one more today. We always do. But other than that, I think we've been having some good stream connection, and I think you're all here. So the first thing I'm going to address is all of the servers are down right now. And I have no clue why that is. I guess I could send them an email and see what's going on. And hopefully they get it fixed. So the thing with code grade is I would like to do late submissions, but I discovered this morning that it will not let you submit after the deadline. It won't let you submit after the deadline. Sigro asks, how long are they normally down? Not this long. And usually not all of them. Usually it's just Bobby and Sally, and then you can get it on cardiac or whatever. But they're literally all of them down. You can't even go to Tux. You can't even go to this website. So I'll keep monitoring it, but you guys all need to have some backup code method. I always use the servers during class, but obviously I can't do it today, so I'm going to be using Visual Studio today. And so I know that there's some issues with the implementation files, how we compile with multiple CPP files. So for assignment 5, if you're still not finished with it, and same with assignment 6, let me think here. For those assignments, if you're using like code blocks, I'm not sure if people have figured out how to do the multiple files thing in code blocks. There's a way to do it in Visual Studio, and I'll try it out later today. But if worse comes to worse, you can actually just copy paste everything in one file. You guys can manage that, right? If you really need to, you can just take all the files and copy paste them into one. And then once you do that, test your code, and then before you submit it to code grade, separate them back out into your files. All right. So as for assignment 6, it's already kind of too late for me to revisit that. But for assignment 7, which I posted today, I won't have you do an implementation file. So for assignment 7, I'll just have you do the header file, and that will be just fine, especially if you're going to be using Visual Studio. I will reach out today to talk to the IT guys, see what's going on there. And just for some of you who didn't get it turned in, today is the late deadline for assignment 5. I actually just made today the flat deadline for assignment 5. So if you turn it in today, you won't be marked late. But I don't think it's going to be, well, I don't think so. It's not going to be available tomorrow. So if you didn't get it turned in last night, and you were planning on doing it today, still do it today. But you won't be marked late because of this server hiccup that we've got going on. All right. And you can always reach out to me if you're having troubles with your own kind of environments. I have quite a few environments on my PC, but I'm kind of a C++ master at this point, so I don't expect you to be up with me, but I do have Visual Studio, and I do have a VirtualBox environment. I don't know if you guys have done VirtualBox environments before, but you can look into those, and I have one of those on this computer as well. So whenever the servers go down, I always have a backup plan, and you guys should always have a backup plan too. Especially if you are saving your files on the servers, you should always download them because of exactly what happened last night. I have no clue what happened, but some of you lost access to your files. And I said that I would be lenient, but if you still can't get access today, you might as well just start assignment 5 over. I don't think it will be too bad. When I was an undergrad, in the operating systems class, I was getting help from the instructor, the professor, and he accidentally overwrote my file and deleted all of my code. And he said to me, "I hope you remember what you typed." And I went back and I sat down and I did it. So chances are you'll have to do it sometime. I'd say assignment 5 is kind of it's a small assignment to do something like that. You just have to do the 1-2-liner functions in the balloon files, and you just have to basically remember your allocation, deallocation functions, all right? So, yeah, I will be lenient, and my leniency is that I'll give you the extra day to turn it in. But if you don't have access to those files, I would say start over. Start over. And I'm sorry about it, but we have to keep moving forward. So now that that's all said and done, I'm going to briefly introduce assignment 7, which I've uploaded as of now. Notice Tux cannot be reached. Alright. So I still don't have the code grade going. I'm working on it. I was wondering why I came over here for that. So I'm still going to work on the code grade, but if you want, you can come over to... Oh, I was going to show you that this is due now today. Alright, so I've changed it. That's what I was going to show you. If you come over to your files and we go look at not the class code, but rather the assignments, I have assignment 7 up. And I'm going to give you some time for this, all right? I'm going to give you more than just a few days. It's going to be due after assignment 6, all right? So you can kind of plan around that. But assignment 7 or assignment 8 will also be coming out in the next 2 days or so. So I've already gone over that, right? We're kind of coming in at the end of the semester here, and I'm trying to get you guys enough assignments. You can use the Terminal Minecraft assignment to help you with the Candy Crush assignment. So I will give it to you guys tomorrow after the assignment's done. And to answer your question, Magum, no, I have no insight. I told you that I will email them after class. I will do that just to see. I mean, I'd assume that someone has emailed them by now. And if I'm the first one, then maybe I can get it fixed. But no, I have no clue. I don't know what's going on there. If we were still, in person, I could just walk down to their office and be like, guys, what's going on? But I'm at home now, so I will send them an email. Yeah. So that being said, let's just quickly look at assignment 7. I said it is a mini one. I mean, it's pretty tiny compared to what we've done before. All right. So this is our templates assignment. That's why we have a chameleon, because templates can take the form, they can change colors, basically. So here's our little chameleon. And all you're going to do... Oh, Dr. Chowder says UNLV had a power outage yesterday. I think that would have exactly something. Thank you for telling me that. That would make sense. I know where the server room is, and they're all hooked up to the power in there, so that's probably what happened. Alright, so I'm not going to take very much time to go over this, but all you have to do is develop a template dynamic array class. Alright, that's all you have to do. It's going to be almost exactly like vectors, alright? You've used vectors before. You're basically going to develop all of the functions that you've used with vectors before. Like I said, there's no special tricks. I saw there was a funny meme someone posted in the Discord today about how we were doing Terminal Candy Crush, right? In this assignment, there's no fun stuff going on at all. We're just making a boring old class. So hopefully that doesn't disappoint you too much. If you do save that header file, you can use it in the future. Instead of having to import that whole vector class, you can just use your own dynamic array class. So here is the UML. Here's the UML. My face is in the way, so I'm going to say goodbye for just a moment. Here's the UML. And so you literally have to do everything in this assignment aside from the main files. Excuse me. So you're going to make the class. I'll show you what the skeleton code is. Where's the skeleton code? Here is the skeleton code. It's empty. All right. It's empty. I mean, I put the libraries in here because I don't want you to mess with that. But yeah, you just have to do the whole thing pretty much. So here's the class. This is what you should be referencing. And notice you have literally everything that you need here. All right, you've got the private, the publics, you've got the what types they are, you've got a few operators, some functions, two constructors, a destructor, and some variables. Whether or not they're constant or static, what type they are. Notice you'll see this type I'm using. This means that it's a template type, all right? So I said consider, let's see, where do I say it? I say consider naming the template type. Yesterday we did type 1, type 2, we did bub sort, we did T1, T2, T3. So for this assignment, consider naming it type, just so you can reference this little bit up here. All right, so that's the template type there. And you have to do, very simple, all right? Very simple. All you have to do is the default constructor, the copy constructor, the destructor, and the operator overload. All right, these three are rule of 3. That's a requirement. And then you just have to do get size, which is easy peasy. Push back, delete at, and the bracket operator. Now guess what? And also you have to do one overload here for the global insertion operator. All right, and that's it. Now guess what? For your strings assignment, you have pretty much done every single one of these functions already. I know you've done pushback, except it's a little different. This one is more just like an insert. But you've also done a delete at, you've done a bracket operator, you have an operator overload and a copy constructor. And so that strings class is basically a dynamic array class, right? But it's just for characters. So for the most part, you can just, develop this and then kind of copy paste your code from that assignment. This you could do definitely within an hour or less. I mean, depending on your C++ skills. I know some of you will probably run into some roadblocks, especially with the templates. But for the most part, this is going to be a tiny assignment, right? There's no tricks or anything like that. And on top of that, I just give you everything as I always do. I tell you exactly what needs to happen in each of these functions. All right. And then look, compiling, you only have to compile main. I guess if you don't have access to the servers, you can't really use Valgrind. But you will have access to code grade. So you can do the memory check. And if the memory check is returning badly, chances are it's not working. I did get a question from Synchro last night, I think, about the memory check. So I'll still have to look at that today to make sure it's working okay. But code grade does have a Valgrind check. So as long as that's working, you can use that. Assuming, of course, the servers don't get back up to speed, right? And then you've got some comprehension questions, which will go in the same format as always now on Web Campus, right? You'll just have to take that little quiz. And then, of course, you're going to submit using code grade. All right, look, that's a little PDF, only 4 pages. And you're just going to develop this template dynamic array class. And that's it. Match the output. All right, that's all you have to do. And so I actually gave you a bunch of, I only gave you one sample output. I'll be sure to give you the rest. But I gave you test 1, test 2, test 3, and test 4. These are all the tests that I'll be running on code grade as well. So you can try to compile with all of these mains if you want. All right. I haven't picked a due date for that yet, but I said it will be due after the other assignment. So probably next Monday or Tuesday. And that's that. Now, I just want to point this out, since we do have a final project also. Let me see here. Since we do have a final project, I kind of want to give you as much time possible to do your work. So this class ends on July 9th. All right, that's the day of our final. And you're going to have 2 more assignments coming out, right? So right now we kind of almost have, we have 2 assignments. We have 3 assignments in play right now and 2 more coming. Assignment 8 will be smaller like this one that I just gave, and then assignment 9 is going to be, I won't say it's a ginormous one, but it is the final project. So I am going to, if you're okay with it, tell me if you're not okay with it, please. But I'm going to make that final project due probably on July 12th. So that does extend past the ending date of the class. But since grades are due on the 13th, I just want to give you as much time to do that project, all right? So the final project will go all the way up until July 12th, all right? So I know that you maybe want that weekend to decompress, and if you're, good at coding, maybe you can get the final project done before then, because I'm going to have the final project ready for you as of Monday, if not sooner. Tomorrow, I'm going to have the recursion assignment out, so you can work on that, and then by Monday, I'm going to have the final project. So within these next 3 days or so, all of the remaining assignments you have to do will be available and active. And I'm going to try to give you until July 12th for that last one. Right, so Coda, that's something I am keeping in mind, is that I want to give you enough time to do it, and I'm not going to make it like a giant one. Like, I'm not going to make you make terminal Minecraft or whatever, but it will just be kind of maybe the same size as, I don't know, say, assignment 2. I would say it was a good one. Assignment 4, kind of around that size. All right, there will be multiple files, there will be multiple classes, stuff like that. But for sure, it will be it will be doable to be finished before the 9th. All right. So thank you for the feedback on that, and you're always welcome to work with me if you need. All right, I'm here to talk to you. I'm not a terrible person, I promise. So I'll do my best to help you out any way that I can. All right, so that's all of our announcement stuff. All right, so if you've got any questions about what the rest of this semester looks like, please bring it up now. Please bring it up now. Other than that, we're going to get started on our recursion stuff. So I'm going to review briefly what we talked about yesterday, and we're going to make some pretty pictures today, and we're just going to do some small little recursion things. All right. So yesterday we introduced recursion. A recursive function is a function where the definition contains at least one call to itself. All right. So I gave you a bad example of this. This will infinitely call itself. This function, if you call foo, it will just keep calling itself over and over again. C++ lets you do that. In fact, pretty much any coding language lets you do that. We talked about Benedict Cumberbatch, right? Mr. Alan Turing, who proved that anything that can be done with loops can also be done recursively. All right, so they're kind of the same thing. But they're kind of in two different paradigms. That's the word I would use. Two different paradigms. And as I was saying in CS202, there really is no cut and dry way for you to look at a loop and be like, I can make that recursive just by moving a few things around. Or by looking at, say, a recursive function, move a few things around to convert it to a loop. There's really no easy way to do that. So we're kind of at this point in time where we don't really have this method. We just have to kind of train ourselves to think about something recursively. And so how do we do that? Well, we have to break things down into smaller blocks. What's the smallest representation of some problem? And I'll go more into detail today with, say, the whiteboard. Recall that recursion is memory intensive and in general slower than iteration. I showed you yesterday when we broke Bobby. Maybe that's why the servers went down, because I asked for the 1000th Fibonacci number. Unlikely, but you did see that, right? Where I went looking for the 1000th Fibonacci number, and it just hanged, right? It just hung there. It wasn't returning. And that's because it was generating a ton of memory, and it is a little bit slower. It was me all along. No, it wasn't. It wasn't. You can just email CS Help Desk or whatever. Tell them that we went looking for the 1000th Fibonacci number yesterday, and that's why there was a power outage. So, remember, if recursion is less efficient than loops, why the heck are we going to use it? Well, some problems are hard to solve using iteration. I'll kind of bring out a little example of that today. It's hard to think about and formulate the solution in these cases while using a loop. And I would say in general, if you're trying to do some iteration on some problem and your loop contains like 10 or more if statements, even then, that's a lot. There's probably a better way to do it, and you might start considering using recursion. Because in these if statements, you're going to be looking for all of these cases. Now, you'll see that recursive solutions are often elegant, simple, general, and easy to code. You saw that little Fibonacci function that we did yesterday? It was pretty tiny, wasn't it? It was small. It was only a few lines of code. And so, as I said, how do we start thinking recursively? Well, we need to take a big problem and break it down into smaller building blocks. All right, and so we're about to go over that. So just remember, what are the 3 things required for a good recursive function? I call this maybe valid. Valid recursive functions always have 3 things: at least one reduction operation, which takes us a step closer to that building block, that base case. We have at least one base case, which is the building block I'm referring to, and it just means that at the base case, the recursion stops. That's when the loop exits, per se, right? That's when the recursion stops. And for a function to be recursive, by definition, it has to have at least one call to itself. Now, there's 2 things that I'll say. There's something you'll hear like indirect recursion. I really don't focus on that in this class. And then there's something called direct recursion. Now, indirect recursion means that the function will eventually call itself from another function. So if you ever hear that, that's what it means. And that, say, foo calls foo1, and then foo1 calls foo. Do you see what I'm talking about? Like I said, I'm not going to spend much time going over that, but you will hear this probably sometime in your lifetime. Functions can be indirectly recursive, meaning that they'll follow maybe a chain of function calls, but then they'll eventually get back around to calling itself again. And then the direct recursion is just the opposite of that, where the function calls itself from its own body, right? The function calls itself from itself. I guess I'll give the example. Foo will call, say, foo1, which in turn calls foo. And in this case, you're going to see foo calls foo. Oh, I did not ask about that. Whoops, sorry. We're getting all caught up doing stuff. Did anyone look at the operators? Or do you want to push it tomorrow? We do have one more day this week. I'm willing to do that. But did anyone look at the operators for assignment 6? Is there one that, is there one or two that you want me to kind of walk you through? Thank you for reminding me. There's a whole lot going on here. Jerry says tomorrow. Is everyone else okay with that? I know we're probably doing a lot of stuff right now. But tomorrow is the absolute last day. So tomorrow you have to come with some operators you want me to do. Otherwise, I'm just not going to do them. All right? Is anyone upset with that if I push it to tomorrow? Honestly, it would work for me better too. Okay. So tomorrow is the deadline. Tomorrow we will do operators. All right? Don't let me forget. Maybe I can put some on your radar. Let me put some on your radar. Here's your radar ones to look at, all right? You can pick whatever ones you want, but here's your radar ones. The ones that you should be asking about, perhaps. I would say your radar ones might be the subtraction in the pluses here. And then maybe one of the Booleans if you want. But I would say your radar ones are definitely the subtraction and the pluses. Other than that, the rest should be easily doable. The multiplication one might be tricky, right? But guess what? You just call concatenation X amount of times. So this one's not hard. But the subtraction and the pluses, put those on your radar. Try them out and let me know if those are appropriate. So, coming back now, let's just kind of finish up what I was talking about. So we're going to do this today. A recursive function's calling sequence can be represented by a tree. So the number of times the function calls itself is how many leaves the tree will have. It's kind of how wide the tree grows. And so we are going to use this kind of syntax here. In that on the, say, a test or on the assignment, if I ask you what kind of tree does this function make, you will say maybe 3 array, 4 array, 5 array. All right, you don't have to go find that name, whatever it is, just like by and un or whatever. You can say if you want 2 array. I don't mind. I know what you mean. And so we're going to do these ones. So we already did the Fibonacci sequence. So what we're going to do is we're going to make the Fibonacci tree. We're going to make the Fibonacci tree. So it's whiteboard time. And I am going to kind of delete this because we're just going to make a new one. All right, I'm going to put the little function up here instead. Let me go get it. All right, so this was our Fibonacci function here. All right, so there's our Fibonacci. I'm going to make this thing a little bigger, and I'll just plop that function right above my head. All right, so it should be fine right there. So attacker asks, how does one determine which type of tree a recursive function is? So it completely depends on how many times the function calls itself. So in the case of this function, how many times do you see it calls itself in one go? Well, here's one call to itself and 2 calls to itself. And you see that this is an expression, so they both have to be evaluated. And so we'll talk a little bit about that as we make the trees. But at most, this function here will call itself twice within one block of code here, right? So if we're looking at the block of code, we've got this little bracket and this bracket, right? And there's no more if-else's hiding anywhere in there. And so it's going to call itself here, and then it's going to call itself again. And so it calls itself twice from one call to itself. So in this case, this is a 2-array tree. This is a binary tree, and I'll show you why. I'll show you why. So I'm going to make a few little things here. Maybe it's a little bit too big, but we'll see how we do. I don't like it. It's a little too large. I like that better. And let me make the text in here big so we can see it. It's maybe a little too small. All right, so this is going to be a call to a fib. All right, that's one function call. And I'm going to put in the n there in just a moment. I'm just going to give it a little bit of a color. And then I'm going to copy paste this guy a little bit. Well, I'll keep one down here just for fun. All right, so let's say we're going to call fib3. All right, we want to find the third Fibonacci number. So I'm going to put it in there. Say we're calling the fib of 3. So this function makes two calls to itself. Can you guys tell me what the ends are for those two calls? Right, you just have to look at the function. If this is n up here, yep, if this is n right here and it happens to be 3, what are the next n's that we see when we come down here? What are the values in this one and in this one? Right, and so what are those values? I'm making you do the math. I'm making you do math. Basic subtraction, 2 and 1, right? So this function here, it calls itself twice. Here it goes. Here's my call. I call myself, and I call myself. And what are the values? Well, we said this is fib of 2, and this is fib of 1. Notice that the tree has 2 leaves. All right, so this is where. Whoa. Any day now. All right. Oh, you know what? I know why my. I officially know why my computer does that. I think every day at 11:56 a.m. my Malwarebytes checks for updates. I think that's what it's doing. Every day at 11:56 a.m. my Malwarebytes checks for updates, and it hogs my whole internet bandwidth or something. So maybe I'll turn that off for tomorrow. I'm gonna write myself a note to turn that off. Stop checking for updates, please. All right, so we're back. Now, what I was saying is that notice here that this is a tree, and I guess if I want to give you guys some terminology, this is like I guess we call it a node. This is the root node. And then these could be considered nodes or leaves. We're going to call these nodes for now. So that's a node. This is the root node, and these are nodes. And notice how the root node splits off into 2, right? 2 things. Where's the camera? 2. So this is a binary tree. You can see that it's splitting off into 2. So, now here's my question to you guys. Is this one here a base case? And if so, what is it going to return? Is this a base case? And if so, what does it return? We're definitely a little bit delayed now, but that's fine. Just catch up with the stream. Is it a base case? Well, look at the function here, right? So here's our base case. If n is equal to 0 or if n is equal to 1. So yes, it is a base case, and it's going to return 1. Yeah, so it doesn't, there's no recursive call within this case, right? So this is the base case. There's no recursive call to itself in here. It just returns n. All right, so this tree here, it kind of stops, right? It says, I'm done. It says, you can have a 1. I'll make these green or something. Here you go. You can have a 1. But fib2, right, that's not a base case. Fib2 is not a base case, right? So it's going to do its thing again, right? What are the values for that one? What are the values? Zero, 1, and 0, right? Are those base cases? Are they base cases? Well, obviously the 1's a base case, right? And you know, I think the 0 is also a base case. You're right. So guess what they return? I want that to be blue, please. Oh, I'm too late. You jerk. All right. So this one here returns a 1, and this one returns a 0. So guess what? Here's how this works, right? Now, what's the kind of, there's an operation that's going on here, right? And that operation is plus. So if you put a little plus between each little level here, you're going to take 1 plus 0 is 1, and then you take 1 plus 1 is 2. What's the third Fibonacci number? Well, it is 2. And so notice that these here are our building blocks. These are our building blocks. It's either a building block of 0s or 1s. 1s or 0s. So the building blocks are the base cases. And as you go up the tree, you're going to kind of combine them a little bit here, right? So it's 0 plus 1 is 1, and then it's 1 plus 1 is 2. And so this up here equals 2. Two is equal to that. And you can see here that this is a binary tree. These here are called the leaves. Let me do that bit here. This is a leaf. All right, the little green numbers are leaves. Those are leaves. So we've got a leaf, we've got nodes, and then we've got the root node. And that's our first recursive function that we've learned in CS 202. Congratulations, everybody. This is fib. So now let's do a few more recursive functions. We're going to do a whole lot today. So to start, to kind of get you thinking, thank you for this wonderful bit. You guys can see this text okay, right? It's decent. The colors are a little bit different, but they're still colors nonetheless. So let's do the power, all right? So you guys should know powers, right? So what does a power look like? Well, 2 to the 2 is equal to 4, right? 2 to the 3 is equal to 8. 2 to the 4 is equal to 16. So on and so forth, right? So that's power. And I know some of you probably import the math function, right? Power, because there's no operator for that. In some languages, there is an operator for that. You might say int x is equal to 3 times 2. Notice C++ didn't like that. But in some programming languages, that is the operator for power. But in this case, we don't have one. So usually you have to make a function for it. So if we wanted to do, we're only going to do integers. And it's an unsigned integer, because powers cannot be negative. Actually, they can be. They can be. If you pass a -1 to it, or whatever. Yeah, Cherry, that's what I was talking about, is CMath, right? You can import pow. So we're going to make that. We're going to make that function. We're going to make it 2 ways. We're going to call loop pow, which, what does it take? Well, it takes an int base, and it takes an int pow, right? So what is that? Well, in this case, it's going to be the base to the pow, right? That's how we think about it. We're also going to make an int rec pow. So one is going to use a loop, and the other one's going to use recursion. I just kind of want you to see them side by side. All right, so I'm just going to do the loop pow for you. It's pretty simple. The first thing you need is maybe an int return value is equal to 1. Because if you take anything to the 0th power, it's equal to 1. You guys should hopefully know that, right? N to the 0 power always equals 1. And so assuming that the power is not negative, well, now we're getting complicated. This is not, let me put a disclaimer. This is integer power. All right, so there's no fractions, okay? No fractions. No fractions, sad face. So I'm not going to do that part. So we're assuming that there's going to be no negative powers coming in here. Let's assume there's no negative powers coming in here. I don't want to confuse anybody. I know some of you are like, well, excuse me, but you can't have a negative power. But I would like to just assume this bit, all right? So that's going to be kind of the base almost. And so we'll do a for int I is equal to 0. I is less than whatever the power is, I plus plus. We can take the return val is equal to itself. So we'll do a times equal base. So let's kind of run that through real quick. So let's assume we've got a 2 to the 2. We're going to take 1 times 2 is 2, and then we're going to take 2 times 2 is 4. So that should work, I think. We could even test it out. We don't even have to like really go to Bobby and wait for the compilation here. This is going to be super fast. Let's see how it works. Cout loop pow 2. And we get a, what does that say? That says 4. All right, we did it. We did it. All right, so I'm okay with that. Does anyone have any questions about how that works? It's pretty straightforward, I think. Now we're going to make this as a recursive function. So I just want to ask a few questions. I know that we're still probably not super confident yet, which is fine. But does anyone have any ideas on what our base case might be for this? Does anyone have any idea on what a reduction operation might be for this? Well, we'll start with the base case. I'll still type it out, but let's just start with the base case. Do you guys have any idea of what that might be? And then, of course, we've got the recursion part of it. All right, so let me kind of give you a hint here. And we're going to break it down into building blocks, all right? So 2 to the 3 can actually be represented as 2 to the 2 times 2 to the 1, which can be represented as 2 to the 1. So notice here I'm breaking it out. How can I make this problem smaller? Which is times 2 to the 1, which is times 2 to the 1. Which can also be 2 to the 0 times 2 times So that's how we can break out a power. Yeah, so Synchro says, I asked, what is the base case? Well, I would say either one you want to do. We're just going to do, let's pretend I didn't do this. Let's pretend I didn't do that one. Let's pretend that, well, I'll go with that, Synchro. You're right. So the base case is when power is equal to 0. All right, so that's going to be our base case. So here's what I'm going to say. I'm going to say if pow equals 0, and what do we do in this case? Well, we're going to return whatever the value is, right? Return 1. Are you guys okay with that? Because remember that anything to the 1 is equal to 0. Now, else, we're going to do something. We're going to do the recursion. We're going to do the recursion. Now, I'll kind of give this one to you because we're still starting out, but I'm going to start asking for more participation as we do some other recursive functions, all right? So this is our base case. This is our base case. That's the most important thing. So now we're going to kind of do the Fibonacci thing. Yes, that's 100% correct, right? So now we're going to do the Fibonacci thing. And the Fibonacci thing is kind of like this. It's 2 times 2 to the 0 in a way. So notice here that this value is the base value. So I'm going to return something times the base. And I'm actually going to make a recursive call to ourself. Now, what do you think a reduction operation might be? So we're still going to pass the base, but are we going to pass the POW, or are we going to do something to it? I have my comment wrong. Oh, thanks. Yeah, let's let's fix that. Thank you. I get ahead of myself, you know. What do you think I'll do to this? Do you think I'm going to pass it back the exact same value? Or do you think I'm going to do something to it? And I'll give you a hint. Here's our first one. Here's our second one. And here's our third one. Yeah, exactly. That's going to be our reduction operation. It's going to be our reduction operation. Yeah, or minus POW. Either one works. I like it this way because we can see exactly what's going on, but you are correct. You are correct. You are totally correct. So I'm going to put that there, POW minus 1, or minus POW, or, yeah. You got it. All right, and then of course the recursion here is this. So based off of this, what kind of tree does this make? How many times at most does this function call itself? What kind of tree do you think it's going to make? How many recursive calls at most does this function make to itself? And Cherry, I will explain that for sure. Let me just make sure we get some input on this. What kind of tree is it? And then I'll explain why it's POW minus 1. Yes, that's exactly right. It's a unary tree. It's a one-ary. So it's a one-ary tree. Very good. And I'll make the picture. It's a one-ary tree. All right, so I'm going to explain now why it's POW minus 1. So the most important part, Cherry, is that we have to get to our base case. So POW will always start at, say, some value, maybe not greater than 0 necessarily. But it's going to start at some power greater than or equal to 0. So maybe we start with a 3. And so we have to work this towards our base case. We need to make the 3 go to the base case. And so if I could show you how this function worked, we're going to take 2. Well, we're going to just say ants maybe. What's the best way to do this? So I was explaining this earlier, right? In that 2 to the 3 can be represented as 2 to the 2 times 2 to the 1, which can be represented as 2 to the 1, 2 to the 1, 2 to the 1, which can be represented as base case times 2, base case times 2, base case times 2. And so what we're going to do is we're going to break that out. So in the first recursive call, it's like this. But then in the next one, we're going to break it out to be 2 times 2 to the 3 minus 1. And then that one breaks out to be 2 times 2 to the 2 minus 1, which then breaks out to be 2 times 2 to the 1 minus 1. And so if we actually go back through here, that's going to be 2, that's going to be 1, and that's going to be 0. And so now we know that this is 1, and this turns out to be 2, and this turns out to be 4, and this turns out to be 8. That's kind of a cool little animation. I should make a GIF. Or GIF. So I know you might still be a little uncomfortable, Cherry, maybe you're not, but the most important part about the reduction operation is that we work towards the base case. If we did +1, we would go off into infinity. We'd go off into the void. We don't want that. We have to work towards the base case somehow, and this is how we're going to do it. So, given that, let's go ahead and test it out. I guess I'll leave that there. I don't see any reason why we shouldn't. And let's see if we get some of the same answers going on here. All right. We did something wrong there, maybe. Or maybe we overflowed it. 10 to the 100 is a pretty big number, isn't it? So that looks right, that looks right, that looks right. And then 10 to the 100 probably overflowed our integer register. Probably overflowed the integer register. So let's maybe try it this one. Yeah, that looks better. Still doesn't look right though, right? You guys understand what's going on there? 10 to the 10 might be a pretty big number. I don't think it ends with an 8. I think our integer register became too small. Our 4 bytes is not big enough to represent whatever this number is. It's too many zeros. All right, so does anyone have any... Yeah, I know, that's right. It is not 10 to the 10. And I'm wondering why, and I think it's because the integer, the variable is too small. It's too small to store it, so it's like doing its best. Do you know what I mean? It's trying to cram that big number into 4 bytes, which it's not being successful with. Do you understand? Is that understandable? What I'm saying? 10 to the 10 is some number, but if I wanted it to be really like that, I would have to make this maybe an unsigned long. Let's see if that does. Let's see if that works. I want to see. Okay, so yeah, it did work, right? This one is still the loop. This one's still the loop, right? This one is still the loop function, but the one below it is the unsigned long. Have you ever heard that before? Do you know about those? Let me show you how many bytes an unsigned long is. Let's see here. An unsigned long is at least, let's see, 16. It's at least 8 bytes. Yeah, I guess it's 8. It's an 8-byte integer. No, it's 16-byte integer. I'm sorry. Sorry. 16-byte integer. 16-byte integer right there. That's what this is. 16 bytes. It's 4 times the size of a normal int. So, that's our first example. Let me add another one here. Yeah, whipping out the big guns, right? All right, this will be recursion 2. And now we're going to do a few more examples. We're going to kind of speed run them, hopefully. But I want to make the picture. Let me make the picture first. I want to make the picture. Wow, I'm sorry that I did that to you guys. Hope I didn't hurt anybody's ears. All right, folks, so this is going to be our power. Save as, PNG is fine. And this is going to be the POW. So what's our POW look like? Well, it's probably going to look a little bit like this. Excuse the terrible formatting. So we're going to have our POW here. So if we call POW 2 to 8, POW 2, 8, should fit. Yeah, that's fine. That's a little too big for what I wanted, actually. 2 to 3 is what I meant to say. 2, 3. So that's going to call itself, right? That's going to call itself quite a few times. I'm actually just going to put them down. This will be 2, 2. This will be 2, 1. And this will be 2, 0. This is our unary tree. Notice that it has one node coming from one node. So one node doesn't split into 2. It only splits into 1. And here's actually a good note. I want to put it in our notes. Recursive functions with multiple, say, nodes, multiple leaves. So we'll say like maybe even 3 array and 4 arrays will be hard to code using loops. In general, it's kind of a good note. The Fibonacci one is definitely doable in a loop, but as the more kind of leaves that this problem represents, the harder it will be to do with a loop. That's a general kind of rule of thumb. So this one is 2, 2. This one is 2, 1. And this one is 2, 0, right? And 2, 0 is our base case. So this base case is going to return a lovely 1, right? It returns 1. And then up here you have this, which was 2 times that. And then 2 times that. And somewhere up there, you're going to have a 2 times that, right? So what you end up with is a 2 times 1, which is 2, times 2 is 4, times 2 is 8. So that's our little unary tree there. I think it's probably best if I move it here. Probably makes a little bit more sense. All right, 2 times 1, 2 times that, 2 times that. And up top, we're going to be equal to 8. So if there's any questions about that, please let me know. We're going to do a few more examples. Now I want to do a log. Do I want to do the log? I don't know if I want to do the log. Kind of want to do I kind of want to do a few. Let's do kind of a fun one. Let's count the number of characters in a string. Is that what I want to do? In a character array, maybe? So let's say we're doing null terminated strings, as we've done before. So let's say I've got my car string, maybe 6, which is equal to, as I always do, my cat, Patty. Now Patty is only 5 characters long, but we are going to null terminate it. All right, that's our string. So let's count the number of strings in this array. So likely this is going to be int length, maybe call it lane, and it's going to take, say, the character pointer, which we've done before, and maybe something else, maybe like this. So what do you guys think maybe a base case for this might be? When will our recursion stop? What's our reduction operation? I know it's kind of a vague question to ask you guys, but we have to start thinking recursively. How do we count the number of characters in a string recursively? How are we going to do it? Let's see what you've got in those brains of yours. And we've got the recursion tree. So look at this character string down here. How do we know that it stops? How do we know when we're done? How do we know when we're done? What do you think? What do you think? Yeah, almost. We're looking for that null character, right? Yeah. So, yeah. That's what I'd say we're looking for. And so let's say we're going to call it like this. So this is going to be the character array starting from some index. All right, so that's kind of what the index is. So let me do this base case here. If string at the index is equal to 0, I'm going to return something. I'm not sure what yet, but I will return something. Remember that this function's an int, right? So I have to return some sort of int here. Else, what do you think we do? Probably a recursive call to itself. And what do you think the recursive operation is? And I might put, say, a +1 there, but let's wait. What do you think the operation might be? What do you think the operation might be? Say we're going to start out here down at 0. Length of string starting at 0. Yes, yeah. So we're getting it, right? A few of us. That's going to get us closer to our base case, right? Because this null character is going to be further out than, say, any of these other characters. Be further out than any of these other characters. So how do we get closer to the base case? Well, we're going to return index +1. And you know what? I kind of want to do this. I want to say this bit here guarantees that we've counted at least one length, right? We've counted at least one character. So if we're going to handle that here, if we counted at least one character, what do you think I should return up here? Do you think that this null character counts as a character in the string? I want this to be length of 5. I want this to be a length of 5. So I'm going to say no, this is not a character. So what do you think I should return here? And then while we're working on it, I'm going to work on our last example for today. We're going to have a lot of fun. -1. Oh, Actually, we have a few. All right, you guys are thinking smart. Let's try the -1 to start. But we actually have a few options here. Let's see what this gives us. Sorry, I gotta run the other one. Looks like we got 4 here. All right, so I'm gonna guess that we return 0, but some of you guys thought of something else, so I will change it up in just a moment. But if we return Z, please stop. I didn't ask you to do that. So if I return 0 there, it looks like I'll get my 5. That's how big it is. But guess what? I kind of like what 420 said. What if instead of doing a +1 here, we just return the index? What do you think about that? That works too. So we have a few options, right? Notice that this index +1 is kind of handling that size bit. And so here we've got a recursive function to count the number of characters in a null terminated string. Right, exactly. All right, so these are some basic ones. I'm not going to make the picture for this one, right? Because this is obviously a unary tree. All right, this is obviously a unary tree. We can tell. And the reduction operation is the index +1. Now we're going to do something really fun. And I hope you guys are ready for it. We're going to do something really fun. And this is somewhere along the lines of the terminal Candy Crush game that we made. Thanks. Let's do that. Let's do that. So I'm going to speed run this, all right? I'm going to do a little bit of speed running. Hope you don't mind. Yeah. So let's say we're just going to make a class for a matrix. We've done this before. We've done this plenty of times. So just stop me if you need me to. But I'm going to make my matrix class. In fact, how about I just go find my matrix class and copy paste it, so I don't have to waste any of your guys' time. I know you probably would like me to take as much time as I want, but I am not going to do that. When did I make the matrix class? Did I do it in operators? I think I did it in operators. There we go. There we go. I'm going to remove some stuff from this code. I'm definitely going to remove some stuff. So I'm going to make it really tiny real quick because there's only a few things I care about. At least for the purpose of this for this example. So I'm okay with the parameter constructor. I'm okay with all the rule of 3 stuff. But I am going to get rid of the operators that we did. And we're actually going to make a recursive function. Okay. Does that work? I think it does. All right, folks, so we have a matrix class here. You remember, hopefully, a little bit of this from when we did operator overloading. Notice we have a double pointer in here, which I would prefer it to be there. We have a double pointer in here. We've got a height and a width, and we've got a few things. We've got a default constructor. We've got a parameter constructor. We've got a copy constructor. We've got a destructor. We've got an assignment operator overload. And that's it. So I'm going to make one more function. Well, I don't have to. Let's make a recursive function here. A recursive print function. So, for a normal void, all right, for a normal print function, let's say we say print matrix. It's going to be constant, of course. And usually, if we're going to do something like that, I think it's pretty common knowledge that we'll probably use a for loop for that, right? I think you guys would agree with that. We would use maybe 2 for loops, and we would say maybe see out this, and then maybe put a nice little space between it. And then every time we hit a new row, maybe we see out an end line. And then at the very end, let's say we see out another end line. So what do you guys think about that? So say maybe I declare a matrix in here, and I want it to be a 4x4. And then if I call m1.printMatrix, hopefully in the terminal, we will see that this matrix prints out just fine. So now we're going to make this recursive, all right? Now, for some reason, my function's not working. And I'm missing something here. I need to figure out what I'm missing. What did I do? How did I mess it up? Probably messed it up somehow. Can I highlight this one, please? Oh! No, I think it's fine. Yeah, so the class is fine. That should be fine. There we go. Yep. So you guys agree with that? So now we're going to make this recursive. Are you ready? Think of your base cases. Think of some other stuff. Now this is going to be in a class, all right? So we're going to get a little bit of a different example here. This is going to be a rec print matrix. It will be constant. And here we go. So let's do kind of what we've been doing here. So this will recursively print our matrix. So we're going to have a base case. We're going to have a reduction op. And we're going to have some tree that this makes. Now, here's how we're going to do it, all right? I'm going to pass in maybe an x and a y coordinate. All right? I'm going to pass in an x and a y coordinate. So usually when we're doing something recursively, we have to pass a parameter. And that's usually where we'll do our reduction operation. So this one's going to be hard to think about. So I am going to give you just a few moments. Let's say we have a 4x4 grid. Now, the thing in the 4x4 grid is, what do you think are the building blocks for this matrix? What do you think are the building blocks for this matrix? What's the smallest thing within this problem? If we're printing this whole matrix, what's the the smallest thing that we can do in actually printing this? What's the tiniest, smallest representation of this problem? How do we break it up? What do you think? The whole problem, right? The biggest problem is to print the whole thing, right? Okay, 0, 0, kind of. It's a hard question I'm asking. So let's see. I would say this is where we would start, 0, 0. But the smallest, like the building block that I'm talking about is that building block would be just printing a single thing, printing one cell. And so our base case will revolve around printing one cell. And how do we know if we can print the cell or not? For example, let's look up here in this matrix. How do we know when we're done? How do we know when we're done? How do we know when we're done? So I think the way that this matrix is allocated is we're going to do it by height and then by width. Let me check. So we're going to do height first and then by width. So I think if, for example, this is a hard one, I know. I think if our height, so I'd say y, if y happens to be greater than or equal to our height, right? Right, exactly. Well, that's how we know we can print it, right? But if the y is, say, greater than the height, here, I'll fix it. I'm sorry, Cherry. I'm confusing everybody. Since I'm doing it like this, I'll put it right there. So let's say if our y is greater than or equal to our height, then we can't print anymore. We've exceeded the matrix. So what I might do here is I might say return. Now notice that this is a void function. This is a void function. So we're not going to return anything. We're just going to return. And 420 asks a 1x1 matrix, right? That's what I'm getting at is, here, let's look at our paint diagram. Notice that the most amount of work that any function call does, say in this power, is it just does one single multiplication, right? So that's kind of our breaking it out into smaller problems. So our one small, like what's the least amount of work we can do in the function? In this case, we're just gonna do 1 multiplication by 2. 1 multiplication by 2. In the case of this function, we're gonna print one thing, right? So I think you and Cherry were all along the right lines there, in that we're just gonna print one cell. We're not gonna print the whole cell. Up here, we're printing all of the cells. But in one function call, we're just gonna print one cell. So we'll say, hey, if we've exceeded the matrix height, we're done. Now, if we've exceeded the width, for example, say we've exceeded the width here, what does that mean we should do? Does that mean we're done, or does that mean we have to go to the next row? Right? So let me make a statement for that. And what do you think we'll do? So if x is greater than or equal to the width, and let's say and y is less than the height, go to the next row, right? So what does that look like? Tell me. If I'm going to do rec print matrix, what's the reduction operator in here? What's the reduction operation in here? If we're going to go to the next row, how do we call it? If we're going to go to the next row, oh, you're right. I'm down with that. I'm down with that. We'll print an end line. But what do we do to our I and j? So in this case, we're going to assume, or our y and x. We're going to assume that our y is equal to 0 and our x is now equal to 5. So now we have to go to the next row. What does the next row look like? In terms of y and x, what does this 0 up here represent? How do we get to that 0 up there? How do we get there? If we're going to go to the next row, how do we call it? Yeah, exactly. That's exactly right. You guys are on the ball, right? You're on the ball. How do we get there? Well, we're going to make our y is going to be a plus plus here. So if you want me to do that one, we'll do a plus plus y. Or if we're going to do it my way, y plus 1. Either one works, right? Y plus 1. And then we're going to reset at 0, right? Remember that I've kind of flopped it because I'm an evil computer science professor. So we're going to do the height here and the width here. Now else, what's the else case? Well, the else case is that we're within bounds, obviously, right? The height hasn't exceeded, and we know the width hasn't exceeded. So what do we print? What do we print? Yeah, attacker, I told you, I'm an evil computer science professor, right? I messed it up. I'm evil. So what do we do? What do we do? What do you think we do? If we're within bounds, what are we going to do? Pure evil, that's me. What are we going to do? We've got 3 minutes left, so we're almost done here, I promise. We're almost done. I just want to know, what do you think we'll do? We're in bounds, right? We're in bounds. We're in bounds here. So we're probably going to do 2 things, right? We're probably going to do some work, right? Yeah, so that's the second part, right? So our recursive call here, we're going to go rec print matrix y plus 1. I wouldn't say that. We're only going to go to the next row if x exceeds our width. But you're all right. You're all along the right path. We are going to do a recursive call. We're also going to print something, right? So since we're running out of time here, maybe you'll pop it out, right? Yeah. So there's one. Cherry says we're going to print it. Yeah. There we go. We're doing it. We're doing it, folks. Yes, exactly. There we go. I'm happy. I'm happy with that. So we're going to print our matrix at y and at x. Say that's good. That's in bounds. That's in bounds. And then we're going to move on, right? And that should do it. That should do it, guys. That should do it. So what's our base case? Well, y will be then greater than or equal to the height. What's our reduction operator? Well, it's either going to be y plus 1 or x plus 1, depending on where we are. And what is our recursion? Well, what kind of tree is this? How many times at most will this function call itself? Take a good look at this. Just gonna run the function to make sure we did it right. At most, how many times will this function call itself? It's a unary tree, right? Now, Cherry, I don't blame you. I don't blame you. There are 2 function calls in here, right? But my question is at most, right? At most. So it's either going to do this one or it's going to do this one, not both of them. So it happens to be unary because it's going to call itself once. I hope that kind of clears that up for you. So that's kind of our recursion stuff. So I'm going to tell you briefly about how the assignment will work. I'm just going to make you solve a bunch of little problems like this. I'm not going to make you, solve the world's like hardest problem using recursion. I'm just going to give you a bunch of little functions to do. There's no kind of like big class. It's just do this little function, do this little function, do this little function. So hopefully you guys will practice on your own with that and kind of get an understanding for how to develop and solve things recursively. All right? You guys are going to get little tiny problems. So that's how that'll work. And then next week we're going to introduce linked lists, and we're going to be using recursion all the time. And there's a recursive function in assignment 5. That's why I didn't have you do the whole assignment. And I will be asking you a few questions about that recursive function in the comprehension questions of the next assignment. So yeah, I hope you're excited. Recursion's fun. I hope you've enjoyed it. All this stuff will go up on Web Campus. This video will go up on YouTube. And that's all I got for you. I hope you guys have a wonderful Friday Eve. Thank you for coming to class today. And I will see you guys all tomorrow. You are welcome. See you later. You're welcome. You are welcome. I'm going to email the CS guys. I'm going to say, hey, how's it going? You are welcome. Have a great day, guys. I'll see you tomorrow. You're welcome. You're welcome.